Welcome to the next part of the Summer Academy, this time compilers. By the way, if you like what you see, make sure to subscribe. Talking about compilers, we need to explain what is compiled versus interpreted. So if you look in the interpreted world, and we're talking here about typical script languages, but also Python, for example, there is what is called a REPL, a read, eval, print, loop. So it literally reads in a certain portion of the code, it evaluates that code, it prints the result out of what had happened, and then it starts all over again. And this is the interpretation loop that you have running behind these interpreted languages. The benefit of this is it's much easier to implement and also to understand how this implementation is working. You also get immediate feedback as a developer, logically. Yeah, you type your command and you get an immediate feedback out of this. And if you think about browser console, for example, this is where you literally, experience JavaScript REPL firsthand. Yeah, you can issue a command and you will get the immediate feedback out of this command. Which brings me to the nice programming environment. It is nice because you can literally try stuff. You can stop your program execution somewhere and simply, inject other code. So it's quite nice as a programming environment. The downside to it is it's actually slower in execution, and this is the reason why most very close to hardware languages are traditionally compiled languages. They are faster in execution and they can optimize much more. So this brings us to the compiler side, and the compiler works more like your code things. You compile them, you link them together, and you execute that stuff. And as you see, this is not like a loop, it is a bit of a sledge. You code, you do your source code. When this is done, you compile it, you link it, you execute it. It digests all of the source code before execution. Yeah, so it's not like you can partly do things or so. You have to literally do the full code, then it's compiled and then it's executed. There is dynamic loading and there are libraries and stuff, but I think for our for the view that I want to bring over here, this is good enough. The biggest upside to this is obviously the faster execution. The downsides are it is harder to implement. So the compiler, for example, is harder to implement because the compiler wants to optimize things, but on the other side, this optimization means it tries to understand the intention of the developer here and changes the outcome based on this understanding of intention. And the problem with this is if the intention is misunderstood, obviously there can be catastrophic consequences without the developer really realizing it, because this is opaque for the developer. You delivered your source code, the compiler did something, and then the outcome was totally not what you expected it to be. Another thing is the delayed feedback, and I've written here source maps as an example. The thing you have to do is you have to understand that the original source code and what is actually running on the machine is not the same thing anymore. So if you want to debug, for example, you need to have debugging information within what is executed on the machine so that you actually can make sense out of it from where it came from in the original source. So this is a bit of an extra complexity that comes with compilers. And what we also have to mention in the JavaScript world is what is called a transpiler or transcompiler. And what it actually does is it takes source code and it compiles source code out of it. And the most famous example in the JavaScript world is Bubble. So what happens in the JavaScript world is that you have a very fast evolving language and infrastructure that is not as fast evolving. So what Bubble does literally is it takes the latest and greatest of the standards and transcompiles it into a version of the language that is less feature rich, but that is actually executable in the infrastructure that you have. The same is true for languages like TypeScript, that is literally taken as a language and transcompiled into JavaScript, which is another language. Okay, so transcompilers, I get the thing, but why should I care as a JavaScript developer about compilers? Because it's an interpreted language. And this is partly true. So what we have in the JavaScript world, and I took V8, one of the wildly used JavaScript engines, as an example here, is we have what is called a Justintime compiler. So as you can see here, this is the pipeline of the V8 engine, and you see we start on the left side with a JavaScript source code. Then we are getting into an element within V8 that is called ignition. And ignition's first task is to reduce the size of the source code and the interpretation that we have of this roughly by 50% by generating what is called bytecode out of this. So we are translating already from JavaScript the source code as it comes in into a bytecode, which is a size reduced version of the program that we have. And the next step that Ignition now does is Ignition looks into the way the code can be generated, and you see this full code gen here on the middle, so to say. What full code gen now does is it tries to identify elements within the source code that can actually be compiled, and by being compiled, optimized. And you see there are two optimization or two kind of compilers that optimize here, Crankshaft and Turbofan. And these both result in optimized code that is then used in conjunction with the not optimized code in an interpreted form. So what we have is we have a just-in-time compilation of elements that can be compiled and optimized this way, and we have other elements that are kept outside of this world that are simply judged as not optimizable in this regard. So obviously what you would like to achieve is to have as much of your code being compiled so that you have a better runtime as well as a better memory footprint. But how can you, so to say, achieve this? And there is some ways that you can help V8 to use more of your code in a compiled manner. So I will give you 3 simple examples here. Example number 1 is we have a class, and the class has a constructor. And as you can see in line 8 and line 9, I'm using these constructors now to generate instances of this class. For the V8 engine, the nice part about this is that it's really easy to understand that this is the same class, and it can literally define one hidden class structure for this and optimize the code to use this one class structure. What happens in line 11 now, or even in line 13, is that in line 11 we are generating a class structure on the fly, which is the exact same class structure that we have with the point class up, but how should our engine tell this? So how can the engine know about the intention of you as a developer that P3 is actually nothing else than a point? This cannot be, so to say, seen out of the code, this type of intention. So help the engine by expressing your intention by using these types consistently and all over the place. Another thing that you should note is that if you take P1 now in line 13 and you add a new property to it, obviously P1 is no longer of the same structure than P2. In that moment, the infrastructure needs to react. It needs to generate a new type of structure. It needs to copy all of the data into this new type of structure, and it needs to keep P1 and P2 as separate entities. So the point here again is make sure you're thinking ahead of time on the complex structures and try to keep them as fixed as possible. Next example comes pretty close to this. What you can see here is we have P1, we have P2, and if the code is executed, actually P1 and P2 are literally the same. But out of the code and the way it is executed, the engine cannot predict this. It cannot read the intention that you have as a developer. Again, this is a bad practice. Try to be very concise in the way you're setting up your structures and you're initializing. Last example for today is monomorphic and polymorphic functions. So I have the classical example here, an add function. So we are saying add, and it's actually x plus y. But this can be in JavaScript a variety of different things. I can give strings, I can give numbers, I can give true and false in that regard, so Boolean. I can have arrays, I can have complex structures in there, so objects. You see there is a variety of different things. For the underlying engine, the best thing that you can do is try to keep the return value, the type of the return value, static in a function. So don't change the type of return value, but rather have one type of return value. With this, the compiler can kick in and can compile this function and literally use the compiled and optimized implementation of this function whenever you're calling this function. So literally your call will be a compiled and optimized version for will be used. If you are going into polymorphic, so you are changing the return type in that regard, the compiler needs to either have the different versions of your functions compiled and ready, and then need to identify on the fly actually which which type of return value comes there. And most of the time this is next to impossible, or it is more it takes more time to do this than simply to interpret the whole function itself. So the point here is try to keep the return type of functions static. So in summary, you can increase the execution times by order of magnitude if you're working against the JIT and not with or for the JIT. And the thing that you need to do to help the JIT to help you is actually to be as predictive and as static as you can be. So don't change things if they are not needed to be changed, and don't change the type of functions in the return value if you can keep it static. This concludes this part of the SummerAcademy. In the next part we will talk about static code analysis, the home turf of DeepCode.